Oh, hi, I'm sorry. My name's Shep Brown. I'm here to discuss thermocouple theory. I met with Dean Mosier last year about his presentation, and he pretty much already discussed the problems I had with some of the theory. So he'd asked me to come in and explain it to you. But I'm pretty sure this is not what you want to hear. My background dictates that I'd be more concerned about the nuts and bolts of it. So please excuse the Seebeck equations and the basis of thermocouple theory. Let's talk about practical theory. To better understand, I would like to do two things. I'm going to talk about the typical modes of thermocouple failure, and then talk about how it should work mathematically, and then let's actually do an experiment and see if it actually does what it's supposed to. So as I'm set up here, I have 9 thermocouple junctions times 2. I've got one set for the TIT indicator, and I've got one set for the temp datum fuel control. What you see over here is collectively the AluMel, which is the negative potential of this millivolts DC, and then ChromL, which is the positive. Here is known as an iso block. This is an isothermic block, and when you're working with thermocouples, you always have to be careful that if you introduce dissimilar metals, you could potentially be creating a thermocouple which would affect all of the overall averages. So they'll have what they call an iso block. So the law of intermediate metals states that you can introduce other metals, such as copper, provided there is not a temperature differential at that connection and where it's being read at. So these iso blocks are used to create that environment. And also you'll understand that when this signal is going in to be interpreted through an indicator or a computer like a temp datum system, there will be a reference junction or an ice bath that references everything down to either 0 degrees C, removing any potential error. So putting that aside, I want to do a series of experiments and then show you graphically how they will actually work mathematically, and then how they work practically. What is represented here is the TC output average of the 9 that normally goes to the indicator is currently at 599.6 degrees. The TC that would normally go to the temp datum currently is at 598.1, both very accurate systems. The rest of these that have the red represent the actual heater probes that we're heating. We have a small offset, as I explained earlier, but each of these heater probes are effectively sitting at 600 degrees each. So what I'm going to do is I'm going to try and simulate as many seated faults as you can, and you'll see the actual effect. Because sometimes there's a little misunderstanding. You can look at the thermocouple theory, as I started to go into, and get a little lost. I am a retired C-130 maintenance officer. I want to know what's wrong, how do I detect it, what's the impact on my system. So with that, I'm going to go ahead and start our equations. I'd first like to discuss a normal situation. In this particular case, we have 9 thermocouple sets. There are obviously 2 I mentioned before, and each of them are exposed to 600 degrees temperature by these heater probes. So consequently, without any error, I should be reading an average of 600 degrees Celsius output. So as I've just explained, we are sitting here with 9 thermocouples all at 600 degrees Celsius, which are being averaged. The reality is, inside an engine, there's a disparity of the temperature, and you saw that in Dean's presentation earlier. So one heater probe might be 5 or 6 degrees different than the other. It doesn't really matter. You have an average, which is exactly how the engine works. So currently, 9 good thermocouples, all at 600 degrees, output 600 degrees. Now what I'd like to do is I'm going to simulate what happens if there's an open thermocouple. People used to say, well, if you have an open thermocouple, it creates a 3.5 degree loss in temperature. Well, that's not exactly true, because some thermocouples may be hotter than the others. If you take it out of the average, then your temperature is going to go down. If you have one that's actually a little bit less than the others and you take it out, the temperature will go up. And if you've got one thermocouple that is actually right at the average temperature and you take it out, you'll not notice. So I'm going to simulate each of those 3 conditions at this time. So now we'd like to take a look at the effect if we have a high-performing thermocouple. Let's pre-assume that number 8 thermocouple used to put out about 633 degrees because it's a hotter portion of the engine or it's a better performing thermocouple. And that the thermocouple here at number 5 is actually substandard, or it's a cooler part of the engine, and it's putting out 566.4. Well, the overall average is still going to be 600 degrees C. However, if there's an open at thermocouple number 8, as I've simulated here, it has a greater impact on the overall average, but in a negative way. So now the average, because we've dropped down to an 8 thermocouple circuit, is 595.8 versus the 600 degrees. Now we've gone ahead and we've found one of the higher performer thermocouples, and you see as we've removed it from the circuit, the thermocouple is now, the overall average has dropped down to 595. So just to refresh the memory, the last one, it went up. This time it went down. Now we'll go ahead and select the thermocouple that will actually stay unchanged. So now let's assume that we're going to have a change in thermocouple output based upon an open. So in this particular condition, we're going to manipulate the thermocouples. There are some that are hotter than others. So instead of all being 600, this time we have thermocouple 1 at 618.4. We've got thermocouple 4 at 581.6. Once again, still doesn't affect the overall average of 600 degrees. Unless, of course, thermocouple 4 is then dropped out of the circuit. So once that's dropped out of the circuit, no longer is it the average of these 9, it's the average of the remaining 8. So you take the 618.4 plus 600 and so on, and the average will then at that point go up to 602.3 with an open thermocouple. Okay, so we had 9 thermocouples all reporting at 600. So we've selected thermocouple number 4 in the system, and we have disconnected the LUML lead to the TIT indicator circuit. So this is simulating as if one of the thermocouples internally had broken and became open. So we were at 600. Now if we look, we're at 602.3. So with an open, we literally went up 2.3 degrees. Now imagine if in this thermocouple circuit I have an open. So let me go ahead and simulate an open on this particular thermocouple right here. So now you can see I've got open leads here. So mathematically, this 600 degrees has been dropped out of that circuit. So before, I had 600 degrees times 9 divided by 9 equals 600 degrees. Now what I actually have is 600 degrees times 8 and then divided by 8 equals 600 degrees. Not real hard math, but when you do have an open, it literally drops out of the circuit and has no impact on the average. Okay, so we've put the apparatus back the way we had it, and we've now removed the LUML lead that goes to the TIT indicator for thermocouple number 7 in this half harness. As you can see here, I'm at 599.4. So basically unchanged. We've got an open, no impact. So once again, review. Sometimes the overall average will go up with an open, sometimes it'll go down, sometimes there's no effect. Now, as I mentioned before, some of the opens and some of the impacts on the thermocouple averaging. Well, you could also have a short. So inside the actual thermocouple housing, there could be a new junction based on the 2 wires touching the actual shroud. We can simulate very easily, and it's also a real-world malfunction, and that is the terminals, the chromial and LUML terminals on the apparatus or on the engine can become shorted together. So let me show you mathematically what should happen. So, and if I'm looking at thermocouple number 2 in my apparatus, and I actually short the chromial and LUML leads, it's pretty warm down there, but it's only 235 degrees C. Well, see, now I have 10 separate junctions. So I've got 235 degrees C, plus I still have all 9 at 600, so that's plus 5,400. Of course, then we divide that all by 10 now, and I end up with 563.5 degrees. So even though I've got 9 good thermocouples in this section, I'm going to see an average quite a bit lower because of that short. Now let's go ahead and do the experiment and see how it works out. Now we've shown the different ways of opens can affect your average. Now we're going to talk about shorts. So as you can see right now, we're sitting at exactly 600 degrees C. So my assistant, Steve Illman's going to go ahead and show you what happens if you should happen to have a short in a thermocouple in a much cooler environment. Probably one of the most susceptible places is inside the thermocouple, but it also can occur at the aft on the lugs. So for our ease, we don't get burned, I'm going to ask Steve to go ahead and short out the TIT thermocouple on thermocouple number 2. Number 2. Okay, thank you, Steve. And as you can see now, significant impact. We're down to 563 degrees. Now realize that that thermocouple could fail inside, or the thermocouple could still be good, but there's something shorting the lugs on the back. Regardless, all they see in the cockpit is 563 degrees. Let's assume he's at 963 degrees, a truer operating temperature. But the temp datum is still seeing 599, or we'll say 1,000 degrees if we're in the aircraft. So here's a bit of a disparity. Temp datum's got one temperature, TIT's got another. Pilot's wanting more temp because he's flying to temp today. He's going to end up with a lot of torque. So now he's going to be sitting there going, that engine's better than it ever has been. Let me tell you right now, engines don't get better with age. Fuel flow being consumed ought to tell you I have a thermocouple problem, and this is how it can possibly happen. So now imagine that I've got good thermocouple junctions, the circuit's fine, but there's some damage to the shroud, because that does happen. So here's this thermocouple installed in the engine, and because of a fracture before installation, or in fact the fuel nozzle's clogged and it's kind of burned up the shroud and it's missing, but the thermocouple junctions are there. I now have airflow coming through the thermocouple mixing with the hot air. So to simulate that, we're going to go ahead and turn off one of the thermocouple heater probes to simulate a cooler output. There's nothing wrong with it electrically, but it's going to produce a lot less thermocouple output. So imagine we do thermocouple number 1, and instead of 600 degrees, let's just say it's cooled down to 303 degrees. And the impact on the overall temperature works out to 568 degrees. So now let us go ahead and do the experiment and see if it supports the mathematics. So I've asked Steve to take one of the thermocouples. Which thermocouple did we turn off?
Number 1.
So number 1 has been turned off. You see how the red light is now gone. So this thermocouple heater probe is down to 303 degrees and it's still continually dropping. The overall effect is 568. So once again, if I have cool air going across this one thermocouple, the overall average has quite an impact. So now imagine we have a good circuit set up, and because of the other potential failures such as conduction, convection, what if there's a radiation issue going on? So I've got all my operating thermocouples at 600 degrees C, but I'm picking up something else in the line. So imagine I take thermocouple 4, 5, maybe 7. I'm picking up a little radiation, and we'll say they're reporting falsely at 700 degrees each. Okay, so now instead of averaging 9 at 600, I've got the 3 at 700. I've got 6 at 600, 5,700. And I divide that by the 9, and I end up with 633.33. So we ought to be able to go ahead and reproduce this experiment using our heater probes by just taking 3 of the probes up to 700 degrees to show you what if you had false input. As I'd mentioned before, there are several modes of failure, one of which is radiation or noise or convection or conduction, any other way of getting an additional temperature or millivolt impact on the overall reading. So to simulate that, I've asked Steve to go ahead and take 3 of our heater probes and crank them up to 700 degrees. So I've got 4, 5, and 7, I've set at 700 degrees to simulate, once again, picking up some radiation or some additional heat. So the overall average at this point now is 635.9, we'll say 636. So this hopefully will give you an idea of the different things that can happen. And next we'll start talking about what do I do, how do I test these thermocouples using the Rolls-Royce specified H395 made by Howell Instruments.